Our second speaker is Frederik Zilly from Bosch. So we have known each other for a long time. When Frederik was in Fraunhofer HHI, then Fraunhofer IMT, then Valeo, or and always in the forefront of depth sensing, stereo, multi-camera, so everything. And now I'm also curious to learn more about foundation models in driver assistance. So please.
Yeah. Okay. Yeah. Thank you very much. Thank you for the invitation, Atanas. It was really an honor to be invited here for me. And as you said, I started in this domain in 2006, by the way, starting with DARPA Urban Challenge. We built a robo-taxi car. At that time, CNNs or transformers were not yet state-of-the-art. But there I fell in love with computer vision, right? And the combination of computer vision and driving systems, is still there. So I will talk about foundation models in driver assistance and cockpit interaction. I will focus a little bit more on the first part because it has also more relation to the audience here with the imaging technology. So is this click? Oh, yeah, okay, sorry, it worked. So what is the problem statement? Why aren't we done yet? There was also the question in the audience, why aren't self-driving cars already rolling everywhere, right? And regulations might be one thing, but the other thing is also the performance, right? Better performance is always preferable, right? There's still the vision to have zero incidents, zero accidents, zero fatal accidents, to bring it down as low as possible and to allow safe mobility for everybody. And the let's say, traditional computer vision, traditional now meaning like CNN-based, is usually trained with bounding boxes, and you have a few object classes like the 80 COCO classes. This is how you train it. But there is a limit of the scene context, of the understanding of the scene interpretation, image understanding, which you can achieve with this. Because to some extent, if you simplify a little bit, the knowledge of the scene is restricted to a discrete set of object classes. In order to overcome it, our aim was to introduce or connect the vision stack with generative pre-trained transformers, GPTs, you know, from the wording from ChatGPT. So in other words, with language models. And what we, the aim for doing this is that there are surprising situations. There are situations which are difficult to, let's say, categorize or put in small boxes, but they're still very relevant. For instance, we have this situation with the ball rolling off the street and the child chasing after the ball, right? So maybe a computer vision system can take the ball. By the way, it might not be part of the classes where bounding boxes existed. A ball is maybe unknown to a traditional CNN system. And what is even harder to do for a traditional, let's say, driver assistance system is to do the reasoning. Yeah? Once a ball has been detected, what does it mean for the scene understanding? There could be that child which was obstructed by the parked car on the right maybe seconds before. But we as humans, when we see this ball, we already start slowing down, right? And we want to train cars to do the same. So surprising situations, many classes, lost cargo. Again, you can train something, you can maybe identify an object, but we as humans, we quickly realize, is this just some paper floating around, or is it a hard rock? Yeah. And also accident situations, everything which is so-called long-tail scenario-ish is difficult to, let's say, tackle with classic machine vision learning methods. Okay, and then in the last years, we have seen the advent of GPTs, but also with foundation models. So for me, it was a little bit when Clip from OpenAI was released, for me, it was a little bit like a new era where image and text would come together. And basically, since then, an evolution, this became its own field of research, how to do it in the best way. And this also has been leveraged by automotive industry. And the idea is to build an ADAS foundation model. With or without text, this can be with text, but also without. But the idea is not to train one CNN with only one type of camera and one type of image information, but basically to throw everything in. Maybe cameras even if automotive cameras with different mounting positions, everything in place so that the ADAS foundation model learns to generalize, right? That is the idea. And then when connected to language models, also to be able to have a better image understanding, to leverage the so-called world knowledge, which we see from language models, because they, on their side, have been trained on vast amount of text data from the internet, like Wikipedia. They will know situations have been described on a text basis, and this information can be leveraged because then it does not need to be learned from image data as well. Not every possible situation which can happen needs to be recorded on the video if you have been able to describe them by text. This is the basic idea. And here I will give a glimpse what is the aim to do. So the aim is, in the first step, to do a better image understanding. And later we come also to two other use cases, basically reasoning, and also at the end of the talk about image cockpit and interaction with the user. So the aim of foundation models, being cutting-edge AI, are to improve the context-sensitive perception and make it reality. And for instance, in a system which is able to understand the scene, here on the left side there's snowy weather, and that it might affect the driving, so inferring that you might need to be a little bit more cautious, or in the center to identify construction zones, right? They're not so standardized, so there's not this one sign construction zone, but in every country it looks different, and an image foundation model can learn it and then draw the right conclusions from it. Okay, so now this is the last slide of the introduction and overview. I give a little bit overview on how the stack looks like. So there's two dimensions if you want. If we start with the top, first of all, this is addressing a little bit how the innovation life cycle works. Martin has also talked about new features are often first integrated into higher market segment vehicles, because new technology often is costly. New cameras cost more money than maybe old cameras. And the willingness to pay in this market segment is often higher. On the other hand, if you develop something only for, let's say, high market segment, you do not get the volume. But for the whole innovation cycle, at the end, you want to have the volume even down to the entry market, so that every car can benefit from safer technology. And this has been done often in the past. For instance, the emergency brake that vulnerable road users, that there needs to be an assistance system to detect persons on the road, needs to be in every car in the EU, right? And this is how it works, right? New technology is introduced, and then over time, it goes down to the different market segments until it becomes a requirement. By the way, there's the same situation also with the night vision. In US, the legislation has changed that from next year on, you need to be able to identify persons on a road even by night, right? And this is opens an opportunity for extra high dynamic range sensors, right? Or using a radar, for instance. Yeah. So this is the, let's say, innovation life cycle on the top. In the center, there's a kind of the stack. So we have the AI perception, which I talked about. Then you have the AI fusion. This can be if you're using different sensor modalities or multiple cameras. This is where you would fuse it. And then in case of self-driving cars, or at least if you have some hands-off driving, you need a prediction and planning algorithm so that the car can be steered by the machine itself. And this is the center line is what we call the system one. And this is a third concept I want to introduce on this slide. This is what is already in the market. End-to-end driving stacks, ADAS driving stacks. And what comes next is the bottom line. This is what we call system two, right? So we have a system one and a system two. This is the terminology from Daniel Kahneman, who says, okay, there is also in our human brain, we have a fast thinking and a slow thinking part. The fast thinking part is the more what is intuitive, what you do all the time, which has been trained. And the system two is the slow thinking part where you need your neocortex more, yeah? You have to think about the scene, right? And this, here we connect more to the language, right? And this is what we are working on here when introducing language models also into the driving stack. The system one will run in real time, and the system two, which helps with scene interpretation, can be a little bit slower, but gives the system one hints from time to time, similar as we are doing it as humans. But okay, this is very high level. Yeah, but okay. So now let's dive into the topic, starting with the video, motivating once more what we're talking about. So there's this situation. You have the large language models to enable the reasoning and context understanding. And now we will see a scene with a ball rolling over the street. And the traditional AI might see that ball. But now with the generative AI, in addition, we have the reasoning capability to see there's a ball and maybe a child will run after it. Or there can be another situation. There is a trailer swerving a little bit, and then the Gen AI could do some predictions, say, oh, the swerving could increase. Do not overpass here, right? I mean, it's kind of an abstract illustration, but this is where we want to go. And the other aspect is make it small. Yeah, language models are known. They work in the cloud, billions of parameters, or trillions even. And this is not suitable for automotive. For automotive, we need to bring it down into a small chip, right? And this is exactly what we have been working on. So now let's depict this a little bit, what we have seen in this demo-ish video. So yeah, we have that input video, and this input video from the front camera in that case, and by the way, I fully agree to Martin, the field of view has increased, and I guess it's increasing, or it will be with multiple cameras to surround vision anyways. But here the input is the front camera, and it's fed into a vision encoder. As we are in the GPT world with pre-trained transformers, this is also a transformer now. It can be trained on billions of images. There are different self-supervised learning approaches out there in the wild. For instance, Dino V2. Now Dino V3 has been released by Meta. And the good thing is it can swallow billions of images. And if you say 1 billion images, what does it mean? Maybe you say, okay, this is a number you will never achieve. But on the other hand, you have the internet on one hand. And if you are doing a driving campaign, we have talked about regulations and in terms of regulations, what you need to do when you release a new ADA software is you need to have an endurance run. You need to show for 10,000 hours that there are no critical incidents. And 10,000 hours at 30 FPS is exactly 1 billion images if you do the math. So by the way, yeah, long story short, if you use one endurance run, 10,000 hours at 30 FPS, you get enough, hopefully enough images, depends on diversity as well, of course, to train that vision encoder. And then you have this vision language connector. I will say a few words in a moment. On the right hand, you have the language model, right? You start with the language model, which is maybe already small enough so that you can distill it later into embedded hardware. And the language connector is trained. It's basically, in the simplest case, it's a projection as a layer, an MLP, which projects from the vector space from the vision encoder into the vector space / token space from the language model, right? In reality, there might be also some more advanced techniques involved, like Q-former, where you learn queries, you learn what to ask for, and backpropagate this into the vision encoder. But this is the rough architecture. And the next thing is, I said, to bring it down into a smaller model. So this is how you start. Then you have your ADAS foundation model, and then you want to bring it down to a smaller hardware footprint. And what you're doing is you are employing methods like knowledge distillation. So knowledge distillation is something where maybe I try to explain it. It's like a teacher-student training approach. I mean, in the first iteration, it could be something like you have an image or you have a driving scene where you want that your small model learns how to cope with it, and your large model is the teacher. Yeah, the large model is already able to do the right thing. You could generate the labels or outputs. You use auto labels from the large model, basically. Use it as a training data for the small model. That's how you can do it. Or you can not only create auto labels, but also transfer all the logits and intermediate layers, so the activations, and learn from the activations, and not only from, let's say, class labels. And this has shown to be a little bit more effective. At the end, you have that smaller model, and it is, click, yeah. And that model can run on this Qualcomm chip. Yeah, there's a Qualcomm PC. It's not a PC, it's just a Qualcomm cube, let's say. And inside there's the Qualcomm 8650, but it can also be deployed on smaller Qualcomms. That is the same chip you would have in the Samsung S24 phone, for instance. And yeah, this is one important step when bringing from a research vehicle on the top right to a pre-series vehicle, let's say, on the bottom right. Exactly. And here we now show that this works. So these were our first attempts. So this was actually generated by a model running on that Qualcomm cube. So you insert some images, and then you see this token by token generation of the output, or autoregressive generation. And with this vision encoder, vision language connector, and language model at the end. And you see that the scene is described properly, and it is not restricted to the, let's say, 80 COCO classes you are maybe familiar with, but it can, let's say, Andrew Ng has also said, okay, with vision language models, every little bounding box can now have its own class, because every little bounding box is described by a text or by a sentence, and every sentence defines a new object class, if you want, right? And now you have an infinite number of object classes, or more or less infinite, right? Okay, so this was running on the Qualcomm Cube. And from there, we wanted to push it a little bit further into this, also, putting the Qualcomm Cube in the vehicle, as shown in the intro video. So at the time of when the video was generated, this was more the vision and the statement of what you want to do. And here we are driving through Stuttgart, where there's often a traffic jam, and you have the correct scene context and the correct description. Yes, and earlier we talked about safety and long tail, and we made a stress test to the system. And here we have a couple of scenes collected where we applied our ADAS GPT, and these are really long tail scenarios. Yeah, so on the bottom left, on the top left, I read for you, the image shows a vehicle that appears to have crashed into a barrier on the side of the road. The vehicle is not in its lane and is positioned against the barrier, which could pose a risk to other vehicles if not removed promptly, right? So, or on the bottom left, the image shows a white vehicle driving on the wrong side of the road, which is a significant traffic violation and poses a high risk of collision with oncoming traffic, right? So this is also like a wrong driver alert. Can also happen on the motorway, right? And also, for instance, here, this trailer on the top right, you see the image shows a vehicle that appears to have overturned or is in a process of overturning on a road, right? So this description is pretty good. And you see a similar image on the bottom right. Is not an accident, right? But visually, for a classic CNN, it might look very similar, right? But there it says, okay, there's a large truck occupying the entire lane on the road. But there's no incident, no critical situation, right? So this is what you can achieve, right? This is so this is the first block, and then 2 small blocks. I have still a few minutes, right? Yeah, okay. So this is what you can do with the image understanding, right? Now, as we have a better image understanding, we can go the next step into reasoning about the scene, right? And how does this reasoning look like? This is a technique. Now we have call it VLA, because before we had the vision language model, and now we say vision language action model. And action means you're closing the loop, you're also generating a steering command, for instance, yeah, or you're affecting the actuators to some extent. So VLA, vision language action model. And what you do, this is a technique from the LLM world, the so-called chain of thought, COT, where basically you get better results than asking your LLM only once. This is also what is behind many thinking models. They are trained using this chain of thought, like DeepSeek and other reasoning models. They learn to, have a sequence of outputs which are then fed as an input for the next iteration. So you start with a scene description, which is now better scene understanding. You say pedestrians are crossing the road in front of the ego vehicle, the traffic light is red. And then you refer. Yeah, you're doing a reasoning. What does it mean? Short-term prediction could be pedestrians will continue crossing the road, the traffic light will eventually turn green. So you generate that sentence, then you ask, hey, what would be a scenario prediction on the midterm? And then you train the system to say, okay, pedestrians finish crossing, the light turns green, allowing the ego vehicle to proceed. More pedestrians may approach the crosswalk, etc., etc., etc. And eventually the traffic light remains red. for the pedestrians, the traffic light, and the vehicle can proceed, right? And then from there, you can finish the chain of thought to say, okay, the ego vehicle is stopped completely to allow pedestrians to cross safely because the traffic light is red, and the meta action would be lateral maneuver, follow lane. This is a, so do not turn left or right, in other words, and longitudinal maneuver would be stop. So don't drive at the moment, and this is how the chain of thought looks like. And let's click once more. And if you go another step further, you can, first of all, you have a different scene here, and now a driving scene. You have also the scene description, the short-term prediction, and the scenario prediction. But here the meta action would be driving, right? Follow lane and keep the speed constant at the end, longitudinal maneuver constant. But the reasoning would be also ego should maintain speed and follow lane to ensure safety with potential pedestrians or cyclists emerging from parked vehicles, right? So this is what the system is able to do. And I will now show also a result video where we have connected this system 2, this slow thinking, to a real-time system which can steer a vehicle, and working both systems together make a better performance. So this is the video the integration was done for the Shanghai Auto Show. We have presented it also there. And you see first the vision language action model, the scene description, and then the action and the reasoning, right? And system 1 is doing the real-time stuff, and the system 2 is, let's say, the higher level reasoning is done by the system 2, and then from time to time, emotion primitive is transferred from system 2 to system 1 to drive a little bit slower, for instance. So we concentrated on a few corner cases. Some of them are related to occlusions, where there's a curvature which might lead to an occlusion of parts of the lanes. For instance, on a highway ramp, there are in the next section there's a highway ramp, and the system will then say, hey, here this might be occluded, reduce visibility, do not drive too fast, because you do not know if there's a stopped vehicle, for instance, after the curvature, or here it's the same. Exactly, traffic congestion also means, drive slowly and adjust the speed to merge to the left lane. So this is what we have demonstrated with the coupling of a fast-thinking system and a slow-thinking GPT-based system. And we had also another LLM running for the real-time translation into Chinese. Exactly. Okay, then let's come to this last block. And this is about the user interaction in the cockpit. So when we started with that GPT, as I said, it was for the better scene understanding and scene interpretation, also reasoning. But then quickly we realized, okay, we have already a language model in the vehicle which is able to understand the scene. That's very convenient because the user also speaks with language models, so maybe they could talk to each other, right? In other words, if you have a machine which understands natural language, that's a big asset, big benefit. And until now, we have seen cockpit systems powered by something like Siri, Yeah, they understand you to some extent, but it's not the full GPT system. And we ask ourselves, can we do something about that? Can we connect our others GPT and bring it also to the cockpit? And yeah, of course it is possible. And I can show some system architecture, what we tried out, and where we had seen that it can work pretty well. And the idea for doing it is, I mean, twofold, or there might be other goals. One is customization. This is also for the OEMs and for the user experience very good if the assistant system knows what kind of persona is in the vehicle. Yeah, that helps to increase the comfort, but also yeah, gives better context. You know better where to drive, etc. This is the one aspect. In addition, there's a second aspect, and this is explainability. So we talked about when will automated driving be a reality, and here I see LLMs also as a potential, yeah, an asset, because they can explain the user what is going on, right? Explainability is a major cornerstone of yeah, releasing safety critical AI systems, right? This is one of the, let's say, yeah, challenges. If you have a full a monolithic end-to-end AI system which does something, then it's only a black box. How do you explain that it behaves safe in all situations, right? It's very difficult. But if you attach a language model and you explain the user all the time what's going on, then the user learns also what the system thinks, learns also what are the limitations of the system, where you want to drive your own and when you can drive with hands off, right? So, and at the end, this will increase the acceptance of the overall system, but also it makes the homologization easier, so to release the system. And okay, here I will show how this agentic AI, as we call it, can work in the cockpit. So at the left, you have the user with voice commands. In the front-end UI, you have speech-to-text, the STT, and in the other direction, text-to-speech. You have the LLM, and the LLM is then transferring the information to the context manager, and the context manager talks to different agents. Yeah, the agent can be about weather services or what is in my calendar today. But another agent can be a vehicle sensor, or what we have just shown, an agent which can drive. It's like a driving agent which connects into this system, for instance, via MCP. MCP is Model Control Protocol. That's a standardized way, or I think it was proposed by Anthropic, how to connect different LLM-based agents together into one agentic AI system. Exactly, and if we drill it down into our use case, then this is how it can look like. So the left part is as the slide before, and as an extra agent, we have our ADAS GPT, we have the input video, we have our generative AI system, and it can then talk to the user. And for instance, the user could say, hey, I want to drive a little bit slower here, right? Or bidirectional, please drive slower. The system can say, please drive slower, there's a ball rolling off the street. Yeah, so it's a bidirectional communication possible. Yeah, and this is the next step we intend to do, right? So with that, thank you for your attention and thank you for the time. Yeah.
Thank you. So there are 2 microphones circulating, and your questions, please.
Thanks for the very nice presentation. So I had one thing to ask. So to train these VLA models, you probably would want a lot of demonstrations of actual humans driving the vehicles to get the like actions, what the user will do in a certain situation.
Yeah.
And if you're a car manufacturer like Tesla, then you have your own cars, you develop your own AI stuff. I saw a recent presentation saying that each day they get roughly 500 years worth of data each day from their fleet.
Yes.
And as you are from Bosch, you do not manufacture your own cars, but I guess you provide these models and components to car manufacturers.
Yes.
So how do you get access to large enough quantities of data to train these models you described?
Okay, yeah, good question, thank you. So on one hand, as you say, Bosch is a tier 1 and works together with many OEMs, yeah, and through partnerships there's also a way to access data in this joint projects. And on the other hand, luckily the amount of data you need is not that high or not as high as a Tesla shadow mode fleet would be able to collect. So let me describe this way. If you have an intelligent system, or let's say an intelligent person, what is the, let's say, cornerstone of intelligence is to be able to learn fast, learn quickly. And in machine learning ways, this would say with a few data points, right? Our GPT model based or powered by an LLM is already very intelligent and is able to learn very efficiently with few data points. Few still needs some thousands hours of driving, but you don't need billions hours of driving, right? At the end of the day, will it be enough? We will have to see, right? But what we can see is that the performance increase per hour of video data plus trajectories is way higher than with traditional end-to-end AI systems. This we can confirm. Yeah.
Okay, thanks.
Hello, I'm Jukka from Amazon Ring. Just extremely interesting presentation, many good aspects. One technical detail, you mentioning this model distillation kind of thing, so that what is the complexity difference from the teaching model versus to this learning model kind of? Can you say anything on that?
Yeah, so the teacher model, I mean, depending on the framework, but one which I mentioned earlier, there's, for instance, self-supervised learning method proposed from Meta, the Dino V2. So they train first a 1.2 billion parameter vision model, and from there they distill down to 20 million parameter models. What we have seen is we had better results if we distill only with models with a factor of 5, yeah, and then maybe even do a second distillation, right? So for us, it has shown to be more efficient because if you have 20 times bigger models, then the logics and the embeddings, they do not look the same anymore, right? Yeah, hope this answers your question.
Yeah, I think that answer is very interesting. Of course, this could be long discussion topic.
Yeah, but we can discuss later, of course, yes.
Yeah, last question.
Thank you for the wonderful presentation. So from the artificial intelligence model and the large language model implementation, And so I was having this thought that we saw the examples of the streets and the roads which are in a very orderly fashion. It's in a very kind of an empty place and all. But how will the accuracy of the model be if it's going to work in a congested street? For example, in a lot of countries and some very highly populated cities, the levels of the traffic and the people or things happening in the street is very unpredictable.
Yes.
So what do you think, or how do you want to present that, how the accuracy of this model and the LLM?
Okay, yeah, thanks for the question. I mean, what is important and is to integrate data from all over the world, right? And this is also how you build foundation models, right? And this is also a value proposition of foundation models, that they can swallow that amount of data. And for instance, we have also a large engineering center in Bengaluru. I was driving there as well on my own. It's a different type of driving, but we have released other systems there as well. So it works. Important bottom line is to have a very diverse data set, not to drive only on the Autobahn for 10,000 hours, but also include exactly the kind of data you are mentioning. Yeah.
Thank you. Thank you.
Okay, thanks again,
Yeah.
Frederik.
Thank you.
And